A main idea is that the brain seeks patterns. So have a look at this example. This is, do you see my cursor? Yes, okay. So you can maybe see some circles in these patterns of this size, but they're moving. They're all over the place once you see them, and there are smaller circles. But there are also other patterns in this picture. There are Maltesian crosses like this. If you follow my cursor, you can see a Maltesian cross. And the picture is also full of Maltesian crosses. Your brain is trying to find some meaning in this picture. And of course, it's made to be not so meaningful. But if you see the circles, you don't see the crosses. And if you see the crosses, you don't see the circles. The brain is looking for patterns here. And the picture becomes almost dynamic because of this search procedure. Here's another example. I guess you see a triangle here between the three circles, but there is no triangle. There are no lines in between here. It's just white empty space. But the brain fills in these line segments to an entire line, so you get this kind of a perception of a triangle. And here is another example showing that the brain fills in a different cultural way. So you can very easily read what's written up there. There's no problem, isn't it? And then you can easily read what's there. But now if I put these two pictures together, you see it looks like that. And then you see that what's up here that you saw as a B, down here you see it as 13, because the context, here it's letters and here it's digits, numbers, and that makes us interpret this visual pattern in different ways. In this context, it becomes a letter. In this context, it becomes a number. And of course, we have learned to read letters and numbers. So this is nothing that is built into us, but the brain has adjusted to seeing this kind of patterns. And that's in psychology, this is called categorical perception. We perceive the categories. So here's another example. We can even construct pictures that seem as if they're moving, even if they're not. And it's an illusory movement. So that's a very quick basic thing about visual perception. And of course, you're familiar with this phenomenon of depth perception. Having these parallel lines make things look further away here. And even if these pictures are smaller, they look like being the same size as the earlier ones here. But if you look at these yellow lines, they are actually equally long. But this one looks much longer because we perceive it as being further away. So that's a visual illusion created by this form of depth perception. And you can play around with illusions and visual illusions in very many ways. And I just played around with architectural ideas on this. There is this old idea of trompe-l'œil where you create something that fools your eye. And this is actually a photo from my own apartment where I'm sitting at the moment. This floor was designed by one of the most famous Swedish architects, Helge Zettervall, at the end of the 19th century. And this is for my living room, and he has created here a trompe-l'œil because this door is much bigger than this small door back here. And this distance is actually only 70 centimeters. But it looks as if it's much further away because it's playing with this idea of depth perception here. So this is a simple example of a trompe-l'œil. And here are some examples from architecture of visual effects that you can create in different ways. I will not go through the details here, but you can see that you can play around with three-dimensional. I mean, it looks like it's moving in different kinds of ways. And I mean, these lines look not parallel, but actually they are parallel, and so on. I mean, these are just some examples of architects that have played around with visual illusions. So that's the background for me. I mean, this kind of visual processing system. Here is an even odder example where they have played around with our visual perception. This is really constructed so everything is upside down, even indoors, I think. Even the flower pots are hanging upside down here. So now with this very quick background, I'm going to my main topic, and that is how objects are represented in the brain. I mean, I'm not just talking about buildings, but about objects in general. And I've written about this a little bit in my book on conceptual spaces. That's a fairly old book by now. And conceptual spaces is an idea that the brain is looking for geometric structures everywhere. You can identify all kinds of properties in terms of geometrical structure. So just to take a classical example, we take the color space, and that has 3 dimensions. It has a hue going from blue and green via yellow and red and back to violet and so on. It's a color circle. And then there is the intensity, and then there is the brightness going from white down to black here. So the color space is a 3-dimensional space. That is how we perceive them. And it's called a space because distances in this space correspond to similarities in our perception. So a blue color is more similar to a green color than blue is to yellow, for instance, because the distance between blue and green in this space is smaller than the distance between blue and yellow. And I've used this kind of idea to model all kinds of concepts, not just objects. And here is another example. The psychologist Roger Shepard showed that this is harmony space, that the 12 tones on a ordinary scale, musical scale, can be organized in the topology looking like a torus. And given this, you can explain how people perceive harmonies. Some tones are closer to another tones and so on. And you can combine them into 3 or 4 tones and make a chord and so on. And Shepard says that this is dependent on our perception of harmonies being located in a topology like a torus. And the third example of a space is the so-called vowel space, how we perceive vowels in different languages. And here, the 2 dimensions involved are the 2 formants, the 2 first overtones of a sound. So if I say ah, it contains 2 and more overtones, but this is the measure of the first overtone in the frequency, and this is the measure of the second overtone in frequency. And phoneticians have discovered that vowels can be represented in this space of 2 overtones, and you find that each of the vowels they are denoted here by E and A and A and so on. They correspond to regions of this space. So my general idea is that concepts are regions in conceptual spaces. That's a very quick introduction to my work on conceptual spaces. I've applied it to very many areas. And today I want to apply it to how we can represent objects in conceptual spaces. And then I don't mean just ordinary space. So we have ordinary space where we move around in 3 dimensions, but objects have structures. And we will look a little bit at these structures. So here is the first attempt, and that is David Marr in his book on vision from 1982. He has these examples where he has built animal shapes from pipe cleaners. And I think you can quite easily recognize these shapes just by looking at the pipe cleaners. But they don't really look like animals. I mean, okay, you know that you can see that this is a giraffe and this is kind of a deer and this is a cat or a fox and that's an ostrich and a rabbit. The only thing you see is basically the elements of the skeletons of the animals. But that's enough to recognize what kind of object it is. And this was David Marr's discovery in a sense that we reduce our perception of shapes into smaller elements. And in this case, he reduced them to pipe cleaners. And an interesting thing from art history is that if you look at very old paintings like rock carvings, they follow more or less the same principles, that you identify people with very simple elements. So these are the legs of a person, that's the arms, and it holds an axe, and maybe that's a shield or something, and that's a ship, I think. So these are typical elements of rock carvings. And down here, there's a picture of 2 horses. They are put in like seen from above, and that's a cart with 2 wheels that also seen from above. I mean, you break down the 3-dimensional pattern of 2 horses with a cart into a 2-dimensional picture. But you see that this is very much pipe cleaner models as well in the rock art. And that means that human perception has some kind of basic idea that these are the most important components of objects. David Moore went one step further, and he said that, okay, these pipe cleaner things we can represent, the one-dimensional pipe cleaners we can represent with cylinders. And a cylinder has two dimensions. It has a length and it has a diameter. And that's all. You can represent a cylinder in two coordinates. And using these cylinders, you can build up basic animal, my cursor is disappearing here, like a quadruped, a biped, or a bird. You combine the different kinds of cylinders in different positions and shapes. And then you can go further and divide the quadrupeds into a cow, a horse, and a giraffe, depending on the proportion of the cylinders. And you can divide the biped into a human and an ape, and you can divide the birds into an ostrich and a dove and other things simply by changing the proportions of the cylinders that are elements in these figures. These are approximations of how we perceive objects. But Moore's idea is that we can reduce these object description into a number of dimensions. So each cylinder has two dimensions, and if you put these together, you maybe get an object containing 16 dimensions, and you can vary the numbers there in a high dimensional space of maybe 12 or 16 dimensions. And then you can describe the different shapes as regions of that high dimensional space. So the cow region of space will be different from the horse region, and that will be different from the giraffe region. But these regions will be more closely together than the regions for humans and for ostriches. So his idea is that we have some kind of spatial representation of objects using high dimensional representations. From a psychological point of view, we don't quite know how these perceptions work. I mean, Moore was the first person working in cognitive neuroscience and trying to find the underlying principles. And he came a bit in the early 80s. Then several other people have tried to do this. Next one was Pentland. He was a computer scientist. And he introduced what he called superquadrics. And David Moore's cylinders had two dimensions. But Pentland's superquadrics have three dimensions. So these are the proportions here of these objects. He introduces other superquadrics. And then he has a limited set of transformations you can make on these superquadrics. You can have linear or non-linear transformations of the shapes and get other types of objects. And then he shows how you can, using superquadrics, you can build up complex objects like a chair like this one. This is built up from superquadrics. So he says that, okay, we get a better approximation of object perception if we use superquadrics instead of using cylinders, and superquadrics plus some transformations. A third person was a psychologist, Irving Biederman, who worked with what he called geons. And these elements are what he thought of as geons. I've forgotten exactly how he defines a geon, but you can see some examples here. And then he shows how by combining these geons, you can make up different kinds of objects. We all recognize them as being built up from smaller parts. So that's an alternative to Pentland superquadrics. And Biederman claimed that this is psychologically more interesting. I will not get into the details here, and they are not so important. But again, they are trying to show that we build up our perception of smaller elements and elements that can be described in rather simple ways using a few coordinates. Another example is from two other computer scientists, Xu and Yui, and they work basically with two-dimensional silhouettes. And what they do is they extract the skeletons. This they do automatically in a computer program. So if you show them a silhouette, you can show them a silhouette of an animal. You can extract the skeleton automatically. But I also assume that these skeletons are built up by some kind of cylinder representation. So this idea they borrow from David Marr. But I also introduced this idea that at each joint here, there is a certain angle where you can turn the tail or the legs. You cannot rotate the legs around the body. The parts are only allowed to change in a certain uh, certain angles, and they partition the animal into pieces. So you see that's a different version of partitioning objects into parts and building them up from skeletons. So these are some examples of how people in psychology and in cognitive neuroscience and in computer science have tried to identify how we perceive objects and how we partition objects. There is no universal solution to this problem yet, and there are new models coming, and computer models are developed to identify and describe objects in this way. But I've given you some examples of how people have been working in this area. Now we get to a different topic. And this picture is from a psychological experiment where subjects, sorry, I have to move there. They were shown real objects. I mean, these are just photos they were made of wood, I think. And they were shown these objects, A1, A2, and A3, and they were told that these are all examples of ancel. And ancel is a nonsense word. It's a word that nobody has heard before, but they are given this name as a category, a name for this category of objects. And then they were shown these objects, S1 and S2 and S3, and they were told that these are all examples of smalt, another nonsense word. And when they have learned these categories, the ancels and the smalts, they were shown a picture like this one, which is somehow intermediate. And then they were asked, is this an ancel or is this a smalt? And the interesting thing with the experiment is that the answer depended on how the experimenter held the object. So if it was held in the middle, like if I can get the cursor right, and in the middle of the object with two fingers, then the subject said that it's a smalt. But if it was held in this end of the object, then they said it was an ancel. It was the same object. The only thing that differed in the experiment was how the categorization, how the object was interacted with. And what the experiment shows is that the categorization depends on how you held the object. So this is another thing that I think is very important, that our perception of objects is not just dependent on the shape of the object, but also what we can do with them. So it's not just perception, but it's also actions that come in how we categorize objects. And I want to develop this idea of action dependence, how our perception of objects is dependent on the actions we can do. And this is called also embodied cognition, because the bodily things the bodily movements, bodily actions get into how we categorize things, how we perceive them. And so the thinking is an interaction between brain, hands, and environment. Now, this is a fairly stupid example of a house. The reason I'm showing you this picture is that in our department and in many other university places, people use eye trackers to find out where people look at objects. They look at other persons, they look at other objects, and so on. And now you take ordinary people and put an eye tracker on them, and then you can see where they are looking in the picture. So my question to you now is, where do you guess that people look at this picture the most? I mean, they look all over it, but where do they focus on it? I'm sorry, but I can't hear your answers. But the answer is that they look mainly at the door. That's where the people focus. So they look a little bit at the windows, maybe at the chimney. They never look at the roof. They never look at the walls and so on. But the interesting thing is they look at the door. That's the focus of attention. So next question is, why is the door so important when you're looking at the house? Well, the simple answer is that that's where you can do something with the house. You can't do very much with the roof. Okay, you can climb on it, but that's the typical actions you do with houses is that you enter them and go out of them, and that you do through the door. And maybe you look in through the windows and out through the windows. But the main interaction with a house takes place via the door, and that's why the door comes so much into focus when people look at things. And this is an example of what Gibson, psychologist J.J. Gibson calls affordances. I think you've heard about this notion before, but I'll talk a little bit more about the affordances of objects here. So they are about possible actions, things you can do with objects. So here is a cup. It has a handle. And this handle affords grasping. I mean, the cup itself affords grasping. But the reason there is a handle here is that sometimes if you have coffee or tea in your cup, then the cup becomes too hot. And then the action of holding the cup becomes uncomfortable. And by adding the air, you can avoid the heat of the cup. So it affords grasping and lifting and drinking from by holding at the ear. And next you have a cup or a mug for a small child. It has two ears because the child has difficulties in doing things, lifting a cup with just only one hand. And this has two ears, so you can, or two handles, you can lift it. And furthermore, this cup has a bib here. You can drink from this. And a cup you can drink from everywhere, and you sometimes spin. And a child may have difficulties in controlling its mouth. So it's much better if there is just a small place where it can drink from. So this bib, this tip here, affords drinking. Yeah? So you see that these objects have been designed to give certain affordances for actions. And Gibson says that they are perceived directly. You don't have to process detailed information. The object tells you more or less what can be done with an object. And it's not created or imposed. I mean, there is no sign on this cup saying hold it by the handle. We don't need an instruction to interact with this object. So yeah, here is another example of affordances. So if you have a thing with buttons, they afford pushing. I mean, you have to learn that buttons are for pushing, but once you see buttons in an elevator or on a door, you know you can push them. Or if you see a switch, like in the middle picture here, you can flip it up and down. And this is something we typically do with turning on and off lights, but it can be used for many other things, this turning on and turning off things. And then the third thing here is the knob, which you can rotate, turn up a volume of a radio, or turn up the light in a room or whatever. So you see these small things here, they afford different actions. You don't want to rotate a button or rotate a switch, and you don't want to flip a knob. They all afford different actions by being designed for our hands. We are supposed to interact them with our hands. We don't flip buttons with our noses or rotate with our feet. I mean, they are made, all these things are made for hand interactions. They afford hand actions. And one of the most famous studies of this is Donald Norman's book on the design of everyday things. I think that many of you have come across this book. So he has this famous example of stoves where you don't know whether this button goes to this heater, or this button goes to that heater. This is an intermediate example because here you have 50% chance of making right. And he has also stoves where you have only 25% chances of making right. And this presumably goes to the oven down below here. This is a photo from I think it's from a hotel in Japan, and this is from the shower in the hotel. It's very nice design, and you can see that they afford gripping by the hands. I mean, you know that you can turn and pull these three things that stick out here, but you have no idea on whether this is hot or whether it's cold or whether it's more water or less water, what happens when you turn these things. I mean, they are not informative. So I guess when you enter a shower like this, you will make a number of mistakes before you learn what the different three objects, what kind of actions or what kind of results they lead to. So that's not, it's an elegant design, but and it gives you affordances, but you don't know the consequences of your actions in this case. So I mean, this is not Norman's formulation, but you can extract from his writings that a well-designed object doesn't need any instructions. You can tell from an object itself if it's well-defined on how you should interact with it. So I think the two cups I showed you are well designed from that perspective. You know what to do with them when you see them. So we shouldn't need instructions for objects. Now, let me generalize a little bit to this. We all know what chairs are. I mean, we all use chairs daily. But as you see on this picture, chairs come in all kinds of shapes and colors and materials and whatnot. I mean, there are so many different kinds of chairs. And so there is nothing in terms of shape they have in common. Not very much, at least. They have, maybe all of them have a horizontal surface and a more or less horizontal surface. But that's about it. So why do we call all these objects chairs? Well, again, this goes back to what they afford. So you can define a chair as it's affording a sitting action with support for a back for one person. So it's a one-person thing. You can sit on it. It has more or less a flat surface. I mean, this is not perfectly flat, but sufficiently flat. And then it has a support for the back. That's what characterizes a chair. You can compare chairs to a stool and a sofa. So what is the difference in function between a stool and a chair and a sofa? Well, if you take the stool first, you can still sit on it, and it's a sitting for one person, but it does not have any support for the back. That's the main difference between a stool and a chair. Then stools can come in all kinds of shapes. And what is the difference between a chair and a sofa? Well, now sofas can come in different materials and shapes and sizes and so on. The difference is that the sofa is typically for more than one person, two or three or maybe even more. And it's not always soft. It can be a wooden sofa as well, but quite often soft. And you can do different things. I mean, this also affords sitting for a person with a support for the back, but it is affords sitting for more than one person. So that's the main difference between a chair and a sofa. But a sofa also affords other things. You can lie down in a sofa. You cannot lie down on a chair or on a stool. So sofa has more affordances than a chair and a stool. And a stool is easily movable. You can move it from one place to another. You can stand on it. You can stand on a chair as well, but it's easier to move a stool to stand on it, and you can unscrew a lamp or do something high up on using the stool as a tool for standing. Chair you can also use for standing and moving. Sofas are not good for standing, and they are definitely not good for moving around to solve other kinds of problems. So what you see is that what is the function of an object? We can define that, and this is my definition of what a function of an object is. this is my definition of function, that it consists of the set of actions that can be done with the object. It has nothing to do, well, not directly, but indirectly it has something to do with the shape, but it's not a shape that's the most important thing. It's the set of actions that you can perform with the object. That's the function of an object. And we can have a look at many artifacts to see this. I mean, the function of a watch or a clock is to tell time, and they can look in a very different ways. The function of a thermometer is to tell temperature, and so on. We have made many kinds of artifacts that look very differently, but they have a similar function. So that's when you are looking at objects, you should not only look at the shape of the object, but also consider the function. And then I have an analysis of actions in terms of conceptual spaces, but that's a rather complicated analysis, and I will not get into that. That depends on understanding movements of and so on, but I will not get into that today. So that's the importance of having involving function as well. And if you look at Donald Norman's work, I mean, you can extract a number of the principles how to design for function. So the first question to ask is, what action should be performed with the object? And this doesn't only apply to everyday objects like Donald Norman is doing, but you can do that when you're designing houses and other things, or places, or open places. And this question applies to all forms of design processes. And that's the question of what actions do we want people to perform with the object we are designing. So when you start a design process, I think you should ask yourself this question: what do we want to do with the object? I mean, a house needs a door, otherwise you can't get into it or out to it. That's a stupid example, but anyway. And then, of course, what cognitive functions are involved. I mean, it's not only that you should see it, but what do you need to attend to? I mean, things that you should attend to should somehow stick out from the object, like the handle sticks out from the cup. I mean, it's something that you can see easily, because that's why that's attention. But you can also have other things of cognitive functions like memory or learning that are involved in the use of an object that you are designing. Many objects need some learning in order to use them, but if the world is ideal, an object should show on itself how it should be used. And then how can they be supported by the design process? How can you support cognitive functions of perception and memory and learning and so on? And as Norman shows in his book, very often when something is badly designed, we make mistakes. I mean, if the Japanese shower is badly designed because we will get too much hot water or too much cold water before we learn how the three control things work. So that's another thing. When you design things, you should also think about how people can make mistakes with the things you're designing, and that should be avoided as much as possible. Okay, I have a final topic, which is the role of forces in perception. I mean, we think that we see shapes, but we see many other things as well. And we actually see forces. So here are some examples. This is you can maybe see what this kind of object this thing is. Now I have to move a little bit here. But I try to give you 200 milliseconds of this. It's a movie. So now you immediately see that it's a person walking. I gave you 200 milliseconds, so that's actually what's needed to identify this thing. And you can see that many things that this person is doing. You get very little information about the person, nothing about the size and so on. You only get information about the body parts and their interaction. I mean, but it's very easy to see. Here he's bouncing a ball and throwing a basketball thing. So how does this work? Well, this was discovered by a Swedish psychologist in the 1950s, Gunnar Johansson. And he developed this kind of patch-like technique where he put small lights on the the joints of the human body. So he had lights here and these points. And then he filmed them in dark clothes in dark rooms. So the only thing you saw on this movie was the dots moving. And what I showed you, the movie I showed you, there were plastic reflective bands instead of dots, but basically it's the same principle. And he showed that within 200 milliseconds, people who looked at these movies could identify the movement and so on. You don't need anything about the colors or the surfaces or the sizes. It's just the movements of these dots that is enough to identify the action. And one of Gunnar Johansson's followers and also I have said that the reason we can do that is we don't only perceive the motion, we extract the forces that generate action. We see that when somebody is throwing, the hand is moving faster than when somebody is waving, even if the movements are quite similar. The throwing involves a greater force than a waving does, for example. So our brains extract the forces behind actions, and that goes automatically. We can't help but seeing the forces in actions. And we do that also on still pictures. So the art historian Rudolf Arnheim, he wrote a book, I think it was about 100 years ago, on forces in pictures. And this is his sketch here. If you have a frame of a picture, we see forces. There is the central, there are the corners and so on. This is his drawing of the forces involved in the picture. And even if you don't have paintings, you can see forces. So I have here two rectangles. And you immediately see that this one is in balance and this is imbalanced. Why do we think that one is in balance? Well, simply because this line is vertical, this line is not vertical. And verticality for us is the dimension in which gravitation works. Our lives are very much dependent on handling gravitation. When we are born, we start crawling when we can move, but then it takes some time to be able to stand up and keep the balance when we are walking and running and jumping and so on. So this notion of balance and handling gravitation is terribly important for our perception of objects. Philosopher Mark Johnson wrote a book on the body and the mind, where he emphasized our dependence on the sense of balance in our own body, but also in our perception of other things. And if there is no balance, we see forces. I mean, we see that there is something happening to this. Either it's falling this way or that way. We can't. This object cannot be standing because it's not in balance. It has to move somehow. We perceive that. And we can go to the arts to have a better sense of this. Oh, I'm sorry, this is the old house again. This is definitely not in balance. I mean, this house, and that's why it looks so terribly odd, because it's an object that's been decided to be more or less out of balance. Here is a painting by Duchamp. And the painting is called Nude Descending a Staircase. This is like a frozen motion. I mean, this is the nude in several steps here, and he's tried to depict these movements. And artistically, it's very elegant. Here is another painting, Jacques-Louis David, painting Napoleon Bonaparte. And this picture is full of imbalance. I mean, the horse is standing on two legs. Napoleon is pointing. There is wind pulling the tail of the horse and the hair of the horse and the mantle of Napoleon. There are mountains that are definitely not in balance. The picture is full of diagonals. Almost no horizontal surfaces in this picture, except for maybe his head here, which is the only still thing. So this is even though the picture stands still, it's a very dynamic picture. We see all the forces, the clouds moving and so on the sky. An extremely dynamic picture that we perceive as being dynamic, even though it's still. So we perceive forces in not only in moving things, but also in objects. And I come back to these houses again. They don't really seem to be in balance. So this is my last picture, maybe. I mean, it depends on you. Just to show that we perceive objects not just by shape, but also by their function and by the forces that we add to them. So this is the building that doesn't look to be in a balance, and this is a little bit leaning as well. Maybe you can note for architects an interesting thing. I mean, this building has the classical principle that if you put smaller windows up at the top, the building looks taller. I guess you know that principle already. In these buildings, the taller windows are at the top. The windows here are taller than at the lower, and that makes the top look even bigger than it is in reality. So these play with windows gives another dynamic dimension to the or dynamic perception of these objects. So I can stop here, but I could also talk a little bit about how these geometric spaces are represented in the brain. I let you decide on what I should do. We can take questions here maybe, and then if there is time, we can go on a little bit more.
Maybe as first, let's step back a little and wonder, why is this important? Why are we talking about this now? Yeah. I think it's because dealing with the world is an intrinsic property of architecture. In the way it is taught to us, in the way we are trained, in the way we approach it. So in that it tries to synthesize its own times. It's an understanding of what is contemporary injected in physical artifacts. Yeah. Physical artifacts of some sort, which provide a support for interactions with that very world. Interaction in this broader sense, not only physical interaction, but in exchange of information. And in that view, I think there are very interesting analogies which can be brought forward between representations in the mind and representations in the world. So between objects that take shape in our mind and objects that we are putting out there in the world as architectural designers. And so following your proposition, Peter, I would like maybe to ask you if we could detail a bit more your ideas about geometry as a domain of representation of thought. If you could give us a brief walkthrough to what brought you to build this idea, or walkthrough through the path from the world to the mind and back that leads to the formation of thoughts in your own perspective, perhaps.
Yes, I mean, I have a background as a philosopher, and in the 20th century, philosophy was very much dealing with language and how language was used in thinking and so on. And everything was reduced to language and logic and to some extent to computer programming. But then I and other people discovered that, I mean, thinking is not just in terms of language. And I was interested in how we categorize objects, how we sort things into animal categories or artifacts and so on. So I was working a lot on categorization. And then I discovered that language is definitely not enough. The logical approach doesn't work. So then I started looking at using geometry to represent different aspects of properties, like the colors or the sounds or the shapes or weight and temperature and so on. And that led me to developing these ideas about the conceptual spaces, where you can analyze different kinds of concepts in terms of geometrical structures. I didn't talk very much about it today, but that's in my books.
Geometry. So do you believe that geometry is an appropriate domain to hold and support the formation of meaning in the mind?
To some extent, yes, I would agree to you. And I have the last few years I've been working with some people in brain science, and animals move around in the world, so they need to have a representation of places where things are, where you can find food, where you can find shelter, where you can find water, and so on. So the brain has developed the hippocampus, which is the organ that takes care of finding places and so on. But so the hippocampus is used to find our way in ordinary space, in the ordinary three-dimensional space. But then people started analyzing what the hippocampus was doing, and it turned out that it's representing many other types of spaces. So nowadays it's a kind of small industry to see that it can represent concepts in many other areas as well. I can talk about that a little bit later if you want to, but that's another connection, that the brain started from using ordinary space and then developed methods for handling other spaces like the color space or shape space and so on. And we don't exactly know how the brain does this now, but there is more and more evidence showing that the brain really does this in some kind of spatial structure, some kind of geometric structure. So in that sense, I think that geometry is quite important for understanding how humans think and perceive the world.